So on to buckling. Now buckling is actually quite a nice quick one to go through. Just a few pointers to raise. So we'll go through that. What I want to demonstrate in the world's most simple model, which is just a tube with a compressive load, is how we define it. I'll just discuss what the options are in terms of what you can consider for buckling, and then we'll look at the results and interpret them. Okay. Buckling, there it is. There's my tube, and there's my setup. So key thing here, got a nice simple model, and what we've got as a load case is a compressive force. In this case, we've applied 1 kilonewton of compressive force at the end of the part, and at this end we've constrained it in 1, 2, 3 and rotations about the axes, so it's essentially pinned, and we've got a 4 rotation by X to stop any singularities. And this node actually has a constraint in Y and Z, so it won't go flying off. So we have a nice simply supported system with a compressive load applied. We've got the results. No, we don't have the results, but we can get them very quickly. There we go. So we've got a nice simple compressive force. I got as far as doing the hand calcs just to confirm that this 5.28 compressive force is what you'd expect for this loading. And what we want to understand is what is the Euler buckling or the linear buckling load factor. So how many times 1 kilonewton will this buckle at? And the way that works, the principle of how it works inside Genesis is you must first have your static loading defined, and then you create a buckling load case that will reference that static load case. So we'll do that in a moment, but because that's the way it works, what that means is your static load case can be essentially as complicated as you like. Anything that we've gone through in terms of contacts, in terms of bolt preloads, if there's thermal loads or whatever the loads are, the buckling calculation is simply working out the scale factor on the total load that you've applied to cause elastic buckling. So that basically gives us good freedom in terms of what we can consider in our case. Happily in this one, it's a very simple one here. So what we need to do to define a buckling analysis is we have to define an eigenvalue method, which is going to calculate the eigenvalues, hence the modes of buckling. So we choose new. Now in Genesis by default, it will use the SMS, which is the super fast modal solver. Now, I personally don't tend to use that for buckling. That's the default for vibration, and I would certainly recommend it for vibration. But for buckling, I would use the Lanczos solver, which is a little slower, but there are some advantages here, which are that, as you'll see when we discuss modal, SMS requires an upper V2 value, which is your upper frequency or upper limit in the case of scale factors for buckling. Whereas Lanczos doesn't need that. So I would like to basically find out the first buckling mode. That's the one that's most of interest. And in this example, I'll try and find the first 3 buckling modes. So if somehow magically it didn't buckle at the first scale factor, what would the shape look like if it buckled at the second buckling mode and third? So we don't really want to have to know what the upper limit on the scale factor is for the load. So using Lanczos allows us to just leave that out and put 3. One other thing I tend to do, so in this particular case, I have applied a compressive force on this member. So we can understand in terms of the principles of buckling that the scale factor is going to be a positive value. I will increase the compressive force until I get an elastic buckling shape. But technically, the scale factor could be both positive and negative. So if, for example, I was to put a tensile force on this member, then it's perfectly feasible for Genesis to calculate that a minus scale factor would then cause a buckling. The first buckling in this case would actually be a negative number. So if we want to discount these load reversals for buckling, then if you put a 0 in V1, that's the lower search range of scale factors, then that prevents that searching for a reversal of the force that would create your first buckling factor. And that's really up to you whether you need that or not. So in this case, we've put 0, so we're not going to look to go the other way, and we've got the first 3 buckling modes. That's all I need to define in terms of additional data for the load case. I can then go to my buckling load case definition. So I'll just do buckling because I have no imagination on my names. I'll choose this buckling load case, and then all you do is you choose that method of eigenvalue that you've just created, and you choose the subcase. That's all you need to do. All the boundary conditions, both the constraints and the loads, any contacts, they are all managed in the static subcase that you've defined. There's no additional boundary conditions to be defined here. It is just performing that calculation of buckling. And the only visual output you've got is your displacement. So I'll request that, and that's present. Good. Okay, so I will solve that. Again, thankfully nice and fast as a solution. So there's 2 things. I'll just load this output file. I'll come back to that in a moment. But equally, I'll just import the out file, the OB2. So if we take a look at what we've got, so the first set of results when I ran it straight away was displacement and stress. So that load case is run again, so I've got displacement and stress. So I can just get rid of those if I don't want them. And I've now got mode 1, mode 2, mode 3, and that's what I asked for. There's a little bit of red herring here. These numbers here are not the load factors, so don't panic if you see a number that's less than a value of 1 that you want. The value that you need to be considering is the eigenvalue that is printed here. Okay, this is in this case 167. So that means that this tube that I've modeled will compress and elastically buckle at 166 times 1 kilonewton, so 166 kilonewtons. That's the buckling force. This frequency, which you see, is actually just a post-processing legacy from modal post-processing inside Design Studio. So it's caught me out in the past. And the way to satisfy yourself of that is if we look inside the out file for Genesis and scroll down, you'll see that what you get is this buckling load factors table printed in the out file. And inside that, you can see the first buckling load factor is 166.6, which is what is tying up in my post-processing screen there. So I say 166,000 newtons is the load at which buckling will occur. So typically what you tend to do is you have a complete load case that's you're analyzing for stress and displacement, and very often you'll run the buckling analysis to just make sure that your load factor is greater than 1, and that just confirms there's no elastic buckling shapes that are happening before stress or displacement becomes your driving factor. Okay, good. So that is, that's our coverage of buckling.